Welcome to the second of 5 videos that have been developed in a collaboration between the University of Melbourne and the Victorian Department of Education and Training. This is the second video and it follows exactly on from the first video where we talked about core number competence. This now moves into primary and secondary maths development and some of the difficulties. So learned symbolic number then is the first stage from the basic number abilities we talked about earlier. And in addition to the basic core systems for exact small number and approximate large numbers, students then develop knowledge about number words, the counting sequence, written number symbols, and also other arithmetic and mathematical symbols, the operations of addition, subtraction, and so on. And then they are ready to go into the whole world of mathematics. And by the time students start school, many have mastered some of these skills, but as I emphasized in video 1, we're going to talk just about a typical development here. There will be a number of students who haven't achieved all of these: counting to 20, ordering numbers up to 9, identifying numerals 1 to 9, comparing symbolic quantities up to 9. Now, counting to 20 is actually, for students speaking English, not as easy as it is in some other languages, because we have a different word for every number up to 20. And so there's a lot of memory needed there to get to 20. Everything becomes regular at 20, 21, 22, 31, 32, and so on. But because of this irregularity up to 20, we do find that some students are not as competent at the counting when they start school, and that was visible in the last slide or second last slide of the previous video, where we saw that there was a set of students who were preschool, but they had poor counting skills but quite advanced other mathematical skills, and a number of them can place a mark on a line to represent a number, and some simple non-symbolic addition. And we saw that in the preschoolers from the previous video. So how do students then progress? Well, once they've mastered counting, they can quite easily progress to simple addition, because counting is just the basis of the development of arithmetic skills for most students. So adding 2 numerosities is equivalent to combining the number of objects from 2 different and distinct sets. And it might look like this. So a student could count the 4 animals in the left and then move on to the 3 fruit by going 5, 6, 7. Or they could say 4 and 3 and then they count with their fingers. But most would just count from 1. Students make use of their counting skills in the early stages of learning arithmetic, and the number words have both a sequence, that is to say they're in an ordinal sequence, and also a cardinal meaning. And it's that cardinal meaning that can present difficulties for many students, particularly those with maths learning difficulties and dyscalculia. And there are 3 main stages in the development of these addition counting strategies. The first of those is counting all. So for 3 plus 5, students will count 1, 2, 3, and then they'll count 1, 2, 3, 4, 5, often using fingers, and then they will count all of them. That is time consuming and also can be error prone. Some students come to realize that you don't really need to start by counting the first addend. You could start at 3. So they start with 3 and then they go 4, 5, 6, 7, 8. So using finger counting, the student will no longer count out the first set, but start with the word 3 and count on. Some students recognize that it's quicker, and also they'll be less prone to error if they choose the larger of the 2 addends to add the smaller. So this time they would select the larger number 5 and then carry on with 6, 7, 8. Now, that more sophisticated strategy depends on knowing that 5 is larger than 3. And we've already mentioned that that is a fundamental problem in the core number ability, the number sense for students with dyscalculia. So early number difficulties then. Well, simple subtraction can also be successfully solved with counting. If we look at this image, we can say cross out 2 pies to find out how many are left, and they cross out 2 and count how many are left. Or cross out 7 leaves to find out how many are left. Students don't have difficulty with this kind of problem. But once we remove the concrete materials or the pictures, it's not always as easy as you might imagine. We often would say it's just the reverse of addition. But this requires the student to understand which particular aspect of addition is being reversed. And particularly for a student who has been doing addition by counting all, reversing that process is not easy for them. So sometimes the language we use can affect the ability for a student to understand what we mean. And we talk about this much more in the 5th video on intervention. So in a normal learning progression then, students learn to multiply and divide after adding and subtracting. And multiplication can also be successfully negotiated by successive addition, either by counting individual objects or by counting objects in sets and combining them. So here we have 4 plates with 5 cupcakes on each. And a student could easily start at 1 and count all of those cakes, one at a time. And a student with MLD may well do this. A more numerically advanced student, though, might count the cakes on the first plate, 1, 2, 3, 4, 5, and notice that there's the same number of cakes on every plate, so they then go 5, 10, 15, 20. What's significant about this is that both students will produce the answer 20. And any underlying specific number difficulties experienced by the first student will not be apparent because they have both answered 20. So parents and teachers often comment that specific number difficulties in maths are not picked up as early as, say, reading difficulties and dyslexia. So why is this, given the evidence presented in the first video that preschool children are already showing differences in basic core number abilities? Well, in part it relates directly to the child's progression into learning arithmetic. Most children are able to count quite competently up to 10 as they enter formal schooling, even though some may count more slowly or be more error-prone. And maths learning difficulties don't really become evident until children need to manipulate numbers in a way that depends on symbolic to non-symbolic relationships. So they need to start to understand the meaning of the symbol. And that is the point at which we start to pick up that children have number difficulties, because if they don't understand the mapping of that number symbol onto a non-symbolic array, so counters or dots, that presents difficulties with working with numbers. And it happens later than you might think. The problem is there early, but revealing it comes later than you think because of this ability just to count. So when do they become more obvious? Well, usually it comes to light when we move from physical objects into symbolic arithmetic. So the student who was able to add this without any difficulty counting the objects is then faced with it like that. And if they don't understand what the numeral 4 represents in terms of that left-hand set, and the numeral 3 represents in terms of the set of fruit there, then they find that sort of problem difficult. And to successfully perform this addition, the student needs to understand the relationship between the symbols and their non-symbolic form. Now we're going to pick this up again in video 5 when we talk about intervention strategies for students with MLD and dyscalculia. But from words to symbols is a really important step in primary school. So typically students will acquire counting words and use them for counting before they learn the numerals 1, 2 and 3 and so on. Once the student has learnt the symbols, the numerals for counting words, there's an important developmental step which is needed, that of associating the non-symbolic form of the number and the word and the symbol. So they need to know that that array of dots is represented by a symbol 5 and the word 5. And in video 3, we're going to talk about where in the brain that association happens and where this neurological deficit is for dyscalculic students. And this mapping of symbols and words onto non-symbolic arrays is thought to be fundamental to number sense and number knowledge, and it is showing that it results in this neurological deficit for students with dyscalculia. And without this mapping, symbols and words have no meaning or any relationship with magnitude for these students. So apart from the mapping difficulties described earlier, the transition from words to symbols can also cause problems for many students, as words in all languages use a name-value system. That is to say, the powers of tens are given special names: 10, 100, 1,000, million. Similarly, in English, multiples of tens are given special names: 10, 20, 30, 40, and so on. But the numerals, by contrast, use a place value system, so that the same numeric symbol can mean different things in different places. So the numeral 7 can represent 70 if it's in the tens column, or 70,000 if it's in the tens of thousands column. And this transition from name value to place value causes difficulty for many students, especially early learners, and can result in them performing 102 and writing it as 1002. So they've written 100 and then they've written a 2. And that is an important indicator of the sort of error patterns that students make when they haven't understood place value. And we're going to discuss these types of errors more in video 4 because they're highly informative about the way students understand the base 10 system of numbers, and we will talk about them in video 5 in the assessment. So base 10 knowledge then relies on understanding relationships between the decimal reference. So what do I mean by that? Well, our system is built up on base 10, so we have 10 units to make a 10, we have 10 tens to make 100, and 10 hundreds to make 1,000. And those images there, the red block is 1,000 little cubes, the yellow cubes are individual, the greens are tens, and the blues are 100. Or we can have them in this sort of form. But these are really useful manipulatives for students because they can be used to perform calculations, they can represent numbers using them, and it can help them understand place value, which is an area which is problematic, particularly for MLD students. Writing numbers is the next stage in understanding numbers. Early in primary school, students learn to write words and symbols representing magnitude, but it isn't always that easy. And if you look on this diagram, and I'll highlight this one here, you can see here that the student was probably asked to write down 2,569. And what they've done is written down exactly that, 2,569, without understanding place value. Here, this student has probably been asked to write down 129, and this student has made exactly the same error as so Sinead has made the same error as Kieran on this task. That is and in fact, Felicity has made the same error as well, although she's put 20,000 in her first attempt at it. So you can see that place value is problematic. And when we're looking at reading and writing numbers and the student's ability to read and write numbers, this is actually our data, 5 to 6-year-old students reading numbers correctly. And you can see here that they are fairly accurate on 8 and 10. They become less accurate. They are accurate on 100, and they regain accuracy to a degree at 200 and 1,000. But you can see that they are highly accurate at the small numbers and at 100. But when we get to numbers like 129, that accuracy drops off fairly quickly. Similarly, when they're asked to write numbers, same idea, the students are just asked to write down the numbers as they're read, and you can see higher degree of accuracy on the numbers 10 or less, and again 100. but you can also see that we have some poorer performance when we get into the larger numbers. So this idea of place value then is quite critical. It is something which we use as an indicator in our clinical research as well. The ability to read and write numbers, particularly to read numbers, is predictive of other issues. And reading and writing numbers is known as transcoding. Now, some people might suggest that in fact this is an issue of attention or tracking, but in fact those sorts of things don't predict these differences. But interestingly, the core number abilities do. So a short subitizing span does also predict performance on these sorts of tasks. So what about older students then? So once students have mastered counting and simple arithmetic problems, they move into a more formal calculation. Problems are presented in symbolic form exclusively and set out with the correct place values. So addition problems might look like this, and these are problems where you don't have to do any carrying. Each of the columns can be added up and they come to a number less than 10. Similarly with subtraction, you can subtract the number and they will all subtract. You don't need to borrow any numbers from the next column along. Students are then introduced to addition and subtraction where they do require carrying if the total of one column exceeds 9, or borrowing if the number being subtracted in any column is the larger. So they might look like this. And in this case of addition, you need to carry. If you do 6 plus 5, you're going to need to carry a 1 across to the next column, and in fact that will also make that column exceed 9, and so on. And with subtraction, you need to borrow from the adjacent column. Now, this requires a real understanding of the base 10 system in order to understand how to reorganize a number to make it possible to do these additions and subtractions, subtraction particularly. And so some of the sorts of known errors that we find are these. Sometimes a student will just take the smaller number from the larger number, whichever, whether they're above or below. So you can see here that that is a student who simply just subtracted the smaller from the larger regardless. They also have this problem with borrowing from 0. They know that they need to cross it out and make a 9 and give it, but they then don't in turn take one of the hundreds. Now, we're going to leave this discussion now, but when we get to video 5, where we look at interventions, we cover this issue in some detail, how to assist students with this kind of subtraction. But also, I want to just emphasize that students with maths learning difficulties and dyscalculia aren't at base 1 for these sorts of problems. So they have already got into difficulties because these sorts of problems don't lend themselves into the normal counting procedures in arithmetic. And that's why it's so imperative that we can intervene to bring them up to a different level so that they have the entering competence for these sorts of tasks. Now, word problems is something which students often groan about, but we do need to just have a look at them. We need to also recognize that word problems and number fact knowledge and arithmetic, they're all overlapping competencies. So word problems aren't something on their own. They are simply testing number fact knowledge and also ability to manipulate numbers. So it's well known that word problems can present a number of difficulties to students. Here's an example of a word problem. Lucy has 3 fewer apples than Julie. Lucy has 2 apples. How many apples does Julie have? And if you had 14 squares of chocolate and 5 chocolate fingers, how many do you have in total? I think they mean how many objects do you have in total? And translating words into symbols is not straightforward. And often students complain that we leave word problems to the last 5 minutes of a lesson. They're often almost like an afterthought, but they're actually a critical part of understanding because mathematical relationships can be expressed in multiple representations, including diagrams and graphs, which we've already seen in these presentations, verbal representations in written and spoken language, as here, and symbolic representations, numbers and letters. And often what students are doing with word problems is representing the mathematical relation, which is now in a written language, into numbers and letters. Interpreting, translating, switching between representations contribute to building this conceptual understanding of mathematical relationships. But that can be difficult. If you haven't got a basic understanding of number and the relationships of number, then trying to take them in different, translating from different formats can be very difficult for a student. And for some students, maybe many in fact, maths may not be about sense making. In fact, Alan Schoenfeld once said that students leave their logical sense making at the door when they enter a maths classroom. And here is an example of it. John wants to make wooden bookcases that are 2 meters wide. He has 2 5-meter long boards. How many 2-meter long boards can he cut from them? And 70% of 11-year-olds answer 5. And they've done that because they've said, well, he's got 2 5-meter boards, that's 10 meters of wood, so he can cut 5 from them, without realizing that you can only actually get 2 from each of the, you're going to have some leftovers. So why do students have such a hard time with maths problems? Well, one important difficulty is that students tend to think linearly in a step-by-step manner and try to make the numbers and the text match each other in the same order. So for example, Jane had 25 pens and she gave away 15. How many does she have now? Translates in a word order 25 minus 15. So that sort of problem is no difficulty for a student. But what if it doesn't follow this step-by-step recipe? So if we have this, after giving away some cards, Jane now has 17 cards left of her original 30. How many cards did she give away? This time, none of these calculations can give you the answer. 17 minus 30, 17 plus 30, or 17 times 30. So the numbers are going to be in a different order for the calculation, and that is where errors occur. Now we're going to cover intervention strategies for word problem solving difficulties in video 5 and suggest a model for intervention based on something called interactive assessment, which I'll describe in more detail at the time, to determine the exact nature of the student's understanding and difficulty. And then beyond the basic 4 rules of arithmetic, addition, subtraction, multiplication and division, 2 areas of maths are well known to present difficulty to older primary school students: fractions and algebra. Now, clearly I'm not going to cover the entire curriculum of primary and secondary education in video 2 because it would take far too long. So I've selected 2 areas that are known difficulties for many students and also those with maths learning difficulties to focus on, because they are often the building blocks for other sorts of progression. So fractions. Fractions are first introduced very early in primary school in the form of students being introduced to the concept of 1/2. They're taught that 1/2 represents one of 2 equal parts of a whole, and most students don't find this difficult. Young children are also used to dividing a pizza between 2 siblings, or even some toys or fruit equally between themselves and a friend. Now, this highlights already a difference in fractions. Fractions can mean 2 things. You could have a group of objects being divided, or you could have a single object being divided. And this distinction starts to impact students' understanding of fractions fairly early. So, it is the case many students never master fractions. So we're not just focusing here on MLD students or dyscalculic students. There are many who never master fractions. So, for example, and this was a study done in the US, when asked whether 12/13 plus 7/8 was closest to 1, to 19 or 21, only 24% of Year 8 students answered correctly. And that test was given about 40 years ago. And then there was work by innumerable teachers, mathematics coaches, researchers, government commissions in all of the intervening years. And then the study was repeated, and this time 27% got it correct. So it is still very hard for students to manipulate those sorts of fractions. And these sorts of difficulties are not limited to just fraction estimation problems, and they don't end at year 8 either. So on standard fraction addition, subtraction, multiplication and division problems with equal denominators, so 3/5 plus 4/5, and unequal denominators, 3/5 plus 2/3, year 6 and year 8 students tend to answer correctly only about 50% of the time. But fractions are foundational to many more advanced areas of maths and science. Grade 5 students' fraction knowledge predicts secondary school students' algebra learning and overall maths achievement, even after we control for whole number knowledge, student IQ, and family education and income. So this was an interesting image I found, and the reason I was interested in it was because we often focus fraction learning to numbers less than 1, and students then are faced with numbers greater than fractions greater than 1, and they're not sure what to do. But this image, I was pleased to see that they've actually included 5 on 4 there, an improper fraction, which helps to make students understand that fractions also go beyond the whole. What is the problem though? Why do students find fractions difficult? Well, there are 3 types of difficulty that you need to overcome when you're learning fractions. First of all, the notation that's used. Understanding the relation A over B is much more difficult than understanding just a simple quantity, like a number. The complex relations between fraction arithmetic and whole number arithmetic. Remember that students will have done a number of years on whole number arithmetic before they reach fractions, and then suddenly there seems to be something different happening. The complex relations among different fraction arithmetic operations, so things like multiplication and division, for example. For example, multiplying fractions involves applying the whole number operation independently to the numerator and the denominator. So that looks like it's exactly the same as whole number arithmetic. 3/7 times 2/7, you multiply 3 by 2, 7 by 7, and you get 6/49. But then, if you try and do the same thing in addition, 3/7 plus 2/7, it doesn't work. So why do we need equal denominators to add and subtract fractions, but not to multiply and divide them? Why do we invert and multiply to solve fraction division problems? And why do we invert the fraction in the denominator rather than the one in the numerator? Now, if I had much more time, I would show you the proof of why we need to invert the denominator rather than the numerator. But that will take much too much time. But if you are interested in contacting me later, I'm happy to show you a proof for that, which students do find somewhat compelling for understanding why we do it that way. Fractions are not always concrete. Although we may start our fraction instruction with objects, perhaps paper folding, plastic fraction pieces, we too often move quickly past these into real-world models, into paper and pencil computation. And even drawings of fractions sometimes can fail to be concrete enough for some students with limited number sense. Our MLD and dyscalculic students really need to be cutting up paper and using manipulatives very long after those that are having difficulties in normally progressing students. So this physical act of cutting, folding, manipulating, it's so important in understanding fractions. And then, of course, to make matters a bit more complicated in fractions, when we multiply whole numbers, we can make groups of objects. 3 times 6 can be represented as 3 piles of 6. So do students really understand what happens when we multiply fractions? And for this slide, I wanted to find an image that would express this. And it was an image presented to students to help them understand multiplication of fractions. And this is what the image looked like. And to be honest, I'm not sure that that is a particularly helpful image for understanding multiplying fractions, but I also think it characterizes exactly what the difficulties are when we're trying to explain multiplication of fractions to students. fraction notation and terminology can also be challenging. We use words like numerator and denominator, and sometimes we forget that students may not have internalized those terms and have most likely forgotten what the words represent. They're unusual terms. They're not something that they're meeting in their environment normally. We need to continually reinforce what we mean by numerator and denominator. Words like equivalence, improper, reduce also add to the confusion. So let's have a look at this image below and try and imagine it through the lens of a struggling mathematician. So there's the image. Both of the yellow fractions represent the same thing, but they're written in two different ways. One, if written carelessly, could end up looking like 2 110. The other is easy to read but difficult to make using technology, and I can concur with that, as I've attempted to always use the horizontal line version of fractions in these presentations using a technology equation editor, and it isn't as easy as just putting a forward slash. How about the purple ones then? Students need to understand that both of those are the same value, 1 7/8, 15 on 8. They are exactly the same. Some students will read that 1 7/8 as 17/8. Even understanding that the 1 is a whole and the 7/8 represents part of another whole can be confusing for many. We need to be constantly assessing for this type of misunderstanding, and students also need to understand that 1 whole is the same as when it's notated with the same numerator and denominator. So we can't assume that understanding is in place, and in the intervention video 5 we will talk about how we can instantiate some of these fundamentals of fractions to aid with progress in fraction understanding for all students. Fractions are just numbers, actually. Do we help students to understand that they are real numbers and even parts of numbers? So when we have a drawing of 3/8, it means we have less than a whole object, or even less than half of an object. Also, fractions allow us to show amounts between whole numbers. In the whole number range, there isn't a number between 3 and 4. If we're talking about fractions, there is a fraction between 3 and 4. An important stage in understanding where fractions fit in our number understanding. So the drawings we use to show fractions are merely representations of numbers from a number line, and maybe putting fractions along the number line may assist in students understanding this relationship between fractions and whole numbers. Now, another area of difficulty, and this is for older students mostly, is algebra. Now, the thing about algebra is we use letters to represent unknown quantities, and these letters we call variables. And terms that have the same letter of variable are called like terms, and they can be combined. And if they have different letters or variables, they're unlike terms, and they can't be combined. So if we look at this image, orange juice and oranges can't be easily combined into any meaningful sum. But if you've got two sets of apples, you can combine them because they're alike. And similarly, you can combine x's, a set of x's with another set of x's, because they are the same variable. In some ways, the problems experienced in learning algebra have commonalities with those discussed previously for fractions. Some of the difficulties that students express in processing fractions results from incorrect application of arithmetic processes. So they've had years of working with arithmetic, and then they start applying those same procedures into fractions. That exact same approach is used in algebra and also results in some problems. So it could be argued, though, that learning algebra is a little like learning a new language. Language in itself is a combination of symbols, such as the alphabet, to express and communicate a coherent idea and message. Algebra, similarly, uses a new set of symbolic notation to communicate mathematical expressions, introducing alphabetical letters to represent variables in a calculation. So This is different from arithmetic, which is about absolute computation of specific numbers. In algebra, students have to visualize multiple possible answers for a given algebraic expression. And I'm going to discuss 4 possible components that might hinder students' understanding when they're learning algebra. So I would refer to these as potential roadblocks in algebra. So the first is this use of symbols to replace numbers. With algebra, students have to visualize multiple possible answers for a given algebraic expression. Whereas 24 plus 7 equals 31 used to be the brand of calculation students would work with every day in school, they now have to contend with this new approach to a mathematical expression where we have 24a plus 7b equals 247, and A and B can represent entirely new dimension in the calculation. And this sort of step into understanding how to introduce these variables can be a roadblock for students. So they need to understand that A and B can be a range of numbers, and it could be integers or rational numbers like fractions. It could be irrational numbers or complex numbers when we're getting into the higher levels of secondary education. So where arithmetic uses real numbers to find an absolute answer, and I'm using the word real numbers there to include fractions, algebra uses symbolic notation to represent a wide range of possible solutions. Students find that difficult because they're used to being asked for an answer. They're used to getting a correct numerical answer. And now they are being asked to really produce something that they would regard as somewhat ambiguous. The next area which we would describe as a potential roadblock is difficulties understanding the equal sign. So after many years of arithmetic, students come to interpret the equal sign as an invitation to perform a calculation. So 3 plus 4 equals tells them that they're going to add 3 and 4 and it's going to give or yield or produce or lead to. So it's the end of the expression. And in order to interpret an equal sign like that, we are going from left to right. So we've got something on the left, we've got an equal sign, and it leads to something on the right. And we see it as one directional. So this equal sign, which is actually a sign of equivalence or balance, and many algebraic equations use it to describe a relationship between and the mathematical characteristics of the variables. In arithmetic, the equal sign is one directional, usually from left to right, and can be interpreted as gives or yields. So, to solve the arithmetic equation 3x plus 4 equals 19, the student would first subtract 4 from 19, reversing an operation or unwinding, and then divide by 3, reversing the operation or unwinding. They're often taught that in order to solve algebraic problems of this sort, they start with the x and they say, what happened to the x first? And what happened first was it was multiplied by 3. What happened next? 4 was added, and the answer was 19. And that's why they use this reversing process. Now, these operations are reversed for the solution of this equation. This equation is actually arithmetic. It may look like an algebraic equation because it contains an x, but actually it's arithmetic because you can apply arithmetic procedures to it. So, could you, though, apply the same procedure to 3g plus 7 equals 4g minus 2? And the answer is no, you couldn't, because this time the equal sign is an equivalent sign. It is balancing the two expressions on the left and right hand side of the operator. So this balancing requires you to actually solve the problem in several stages by performing the same operation on both sides. So algebraic problem solving with equations is different from arithmetic because the equal sign means something different. Although, in fact, the equal sign has always been an operator of equivalence. It's simply that it has not been interpreted that way in arithmetic. And then we come to algebra word problems, which of course are even more complicated than arithmetic word problems because we now have some unknown values that we've got to accommodate, and you need to designate those with some sort of a letter and then build up the mathematical relationships in the problem eventually to produce a symbolic equation. For example, Ellie has 4 times as many 20-cent pieces as 50% pieces in her piggy bank. She has a total of $10.40 in her piggy bank. How many of each type of coin does she have? So apart from trial and error, how might you solve this? Well, you might say, well, let's let the number of 50-cent pieces be X, or any other letter. Now we know that there are 4 times as many 20-cent pieces as there are 50-cent pieces, so there'll be 4X 20-cent pieces. And if we add those together by making the number of cents, so remember 50X and 80X, because there are 4 times, 4X there, the total of that is 130X cents. And now we're going to divide $10.40 by 130X and get that X is 8. That is a lot of steps in problem solving in order to get the answer to that problem. And we would then say Ellie has 8 50-cent pieces and 32 20-cent pieces. So simply constructing an equation to represent this algebra word problem requires many steps, and there are many places for a student to go wrong along the way. And it's often hard to find out which stage in the problem solving process the student was unable to complete accurately. So in video 5, we're going to pick this up again in this discussion of interactive assessment, which is an intervention strategy that assists all students to achieve success in many of these sorts of aspects of maths by breaking it down into these steps and also providing support for the student when they go wrong. So why does algebra matter? Well, algebra is critically important because it's often viewed as a gatekeeper to higher level mathematics, and it's a required course for virtually every post-secondary school program. When students successfully make the transition from concrete arithmetic to symbolic language of algebra, they develop abstract reasoning skills necessary to excel in maths and science. So the take-home message for this video is that we've focused on the development of number beyond basic number and preschool number abilities through primary and secondary school to the more advanced maths competencies involved in fractions and algebra. It's important to note that the sorts of known errors students make in advanced arithmetic, fractions and algebra are not confined to MLD students. Many students who don't have specific maths learning difficulties can experience problems in these areas. However, the basic number deficits characterizing MLD students impact significantly on more advanced arithmetic processing, fractions and algebra. For example, a lack of understanding of the base 10 system, which is commonly associated with MLD students, results in their inability to successfully add multi-digit numbers involving carrying or subtract multi-digit numbers involving borrowing. This is going to be addressed, as I've repeatedly said, in much more detail in video 5, when we're going to look at intervention strategies for MLD students and students with dyscalculia in these more advanced mathematical domains.